Okay, let's solve the following improper integrals. First we have the following integral of 1 over x from 1 to infinity. So that's very easy integral in fact, but this infinity makes it a little bit difficult. So if you draw the graph of 1 over x, this is the curve, and everything that we are trying to find, this integral can be seen as this blue region. So what is the area of this blue region? So as we know, with improper integrals where we have infinity as a limit of integral, the idea is to replace this with t and take the limit as t goes to infinity. So let's do that. So first I'm going to write it as integral from 1 to t 1 over x dx. So the integral of 1 over x is ln, so that makes it ln x from 1 to t. If I plug the boundaries, you get ln t minus ln 1. So now let's take the limits. If I take the limit, if I send this t to infinity, so it's going to be my integral from 1 to infinity 1 over x dx is going to be limit as t goes to infinity ln t minus ln 1. So, and we know that the ln function goes to infinity as t becomes larger and larger. So this limit diverges. So this limit becomes infinity. So it means this is divergent. So which means the following integral is divergent, and the area under this curve over here and the area under this curve over here, this is infinite. Okay, the second problem is the following. So we want to take the integral of x times ex from negative infinity to 0. So the lower boundary is negative infinity. Again, using the same. So we are going to use the property of improper integrals and set this to be t, and after finding the integral we can take the limit as t goes to negative infinity. So let's evaluate this integral. So this integral is not a simple one. We have to do partial integration. So let's recall what was partial integration. The formula for partial integration was uv dv is equal to uv minus integral of v du. So if I want to do the integral from my problem, so it's from t to 0, t goes to negative infinity, x ex dx. So I'm going to write x, I will say that u is x, dv, so in partial integration dv is ex. That means du is equal to 1 because du is the integral of u, just 1, and v is ex because dv should be the integral of. If I plug it to the partial integration formula, I will get, so first I have to multiply u and v, so here u and v, that's x times ex minus integral of v du. I have to multiply v to du, so v is ex, du is 1, so that's basically integral of ex. So integrating ex is a very straightforward. So the integral of ex is ex, so I'm going to replace that with ex immediately. Ex, so that is an integral from 0 to t. Okay, now I can erase this part, and if I plug 0, I will get 0 times e to the power 0 minus e0, subtract t times e t minus e to the power t. So simplify this expression. By simplifying, we get this is 0, this is 1, so that's negative 1. And let's take out e to the power t out of the parentheses, so that In that case, we will have e to the power t, here 1 minus t. So note that we have positive sign right now. We have positive sign instead of negative. That's because I wrote it as 1 minus t, not t minus 1. So the integral of this part turns out to be negative 1 plus e to the power t, 1 minus t. So what I'm going to do is take the limit as t goes to negative infinity and limit as t goes to negative infinity. So that's a very simple task. So if I take the limit of this function as t goes to negative infinity, so I'm not going to evaluate this, just see the intuition behind this, because this negative 1 is still negative 1, stays as negative 1, right? It's a constant. But this 1 minus t, that becomes t is negative infinity. With this negative sign, this becomes infinity number, but it's a linear. Okay? And what about e to the power t? Since e to the power t, it's exponential number, but the power is negative, so this number becomes 0. So basically what we have is 1 over exponential number. So this is 0, but it's an exponential 0. So when you multiply them, you get total of 0. So the final limit is going to be just negative 1. So that makes this integral is negative 1. Okay, here's another improper integral, 1 over 1 plus x squared. This time the both boundaries of the integral are infinities. So here is the graph of the curve, and this integral represents the area under that curve. So we expect that area to be pi. So if you do if you solve this integral, the result is pi. So the trick here is to split the integral into two separate improper integrals. So the first, you can rewrite the integral as so that everything is equal to. So I will choose 0 as splitting point. So integral from negative infinity to 0, 1 over 1 plus x squared dx plus the integral from 0 to positive infinity, 1 over 1 plus x squared dx. Now we can compute these integrals, both of them separately, and then add the final result. So let's do the first one. So if I do the integral from 0 to negative infinity, 1 plus x squared dx, so I will have to replace this infinity by t and take as t goes to negative infinity. So integral of, we know the integral of 1 over 1 plus x squared. So the integral of this, so this part is basically arctangent function. So arctan, so that's from table. So you can look up from the table. From t to 0 and t goes to negative infinity. So if I plug arctangent 0 minus arctangent t as t goes to 0, so that will give me, so since arctangent 0 is 0 and arctangent t as t goes to negative infinity, it's negative pi over 2. So the result is negative pi over 2. So that's just pi over 2, which means the first part of my integral, so this part of my integral is pi over 2. Let me integrate the second part. In the second part I have the same integral, so I'm not going to erase everything because it's going to be very similar. In the second part I have different boundaries, so it's going to be from 0 to infinity, and the integral of 1 over 1 plus x squared is still arctangent, but we are computing that from t to 0 as t goes to infinity. So that means I will have arctangent t minus arctangent 0. So arctangent 0 is 0 And as you can see, as t goes to infinity, arctangent t will be approaching to pi over 2. So that makes the second part of my integral is also pi over 2. In total, this part pi over 2 and this pi over 2, the result of this integral is going to be pi over 2 plus pi over 2, which is just 1 whole pi. So this integral of 1 over 1 plus x squared from negative infinity to positive infinity represents this curve, and as we found, pi is the area under that curve.